In Chapter 3, we'll be looking at alkenes and alkynes and how they can become parts of organic reactions. In the picture here you see flamingos, and if you're not familiar, the color of flamingos, that pink color, comes from their diet, which consists of beta-carotene. You can see the structure of beta-carotene there has several double bonds, and that is a chemical compound that is responsible for that pink color in the flamingos. So why should we care about alkenes? We already know that alkenes have carbon-carbon double bonds. They're present in most organic and biological molecules. They are hydrocarbons that contain a carbon-carbon double bond, like I mentioned. This includes many naturally occurring materials, so that we can see them in fragrances, vitamins, and other flavors. One that you might be familiar with is ethylene, which is the 2-carbon structure here. That is a plant hormone that induces fruit ripening. So that gas that's given off in your bananas is ethylene, causing it to ripen. Ethylene is a plant hormone that induces fruit ripening. Pinene, the structure of alpha-pinene here is in turpentine. Beta-carotene is that orange pigment and vitamin A precursor. So you might see this in carrots. An alkyne is a hydrocarbon that contains a carbon-carbon triple bond. These are less common than alkenes. The simplest one that you might come across is acetylene, which you might know is the gas that is used for welding or for blowtorches, and that is just 2 carbons, also is called ethine. When we name alkenes and alkynes, we want to name the parent as we did with alkanes, except now we use the -ene ending. We want to find the longest carbon chain, which is 5 carbons long. This is a pentene. And the longest carbon chain must contain the double bond. So both of these structures are the same. This one is named as pentene because it's 1, 2, 3, 4, 5 carbons. And both of those carbons in the double bond are contained there. This one has a 6-carbon longest chain, which you think would make sense as the longest carbon chain, but both of the carbons in the double bond are not contained, so this would not be a hexene. We also want to number the carbon chains so that the double bond carbon has the lowest possible numbering. So for the numberings here, if we number 1, 2, 3, 4, 5, 6, this gives the alkene at the 2 carbon. So if we number it from right to left, where the double bond starts at 2, in the other direction, the double bond starts at 4. So you want the lowest numbering possible. In order to do that here, in this case, if we number it from left to right, we get the double bond starting at 3. If we number it from right to left, the double bond still starts at 3. So in that case, you would think that it would be the same either way, but you want to think about the substituent here and giving that the lowest numbering. So the 1, 2 direction would be the lowest numbering here. Then we write the full name. So you number substituents according to the position in the chain and then list them alphabetically. So this structure here, it's numbered from right to left. Double bond starts at 2, which is where you put the number. So this is 2-hexene. The one that we saw in the last slide is 2-methyl, 3-hexene. And you list the location of the double bond right before you have the hexene. So notice that it has the -ene ending there for alkene. This structure here we said was pentene. We saw that one earlier. This would be 2-ethyl, 1-pentene. You could also list 2-ethyl pentene, and that would assume that the double bond starts at 1. This structure here is 2-methyl. We have 2 alkenes, so you would list where both of those start. This is 1, 3. Bute is the parent for a 4-carbon chain, so this becomes bute. We take the O from butane. We have 2 alkenes, so we use diene. So this one is 2-methyl, 1,3-butadiene. If you have a cyclic structure, just like with cycloalkanes, we're going to name it as a cycloalkene. And the double bond is always assumed to start at 1. So it's going to be 1 all the time. So this structure here becomes 1-methyl cyclohexene. This here, if you have 2, would be 1,4-cyclohexadiene. or you can name it cyclohexane. This structure here, the double bond needs to be between 1 and 2. So this would be 1,5-dimethyl cyclopentene. For naming alkynes, we use the same rules, but instead we use the -ine ending, which indicates an alkyne. The same things apply. We want to give the alkyne the lowest numbering and then list the substituents and the numbers where they're located. This is 6-methyl. The octine or the alkyne starts at 3, so it's 3 and then octine. You could also name it 6-methyl oct-3-ine. You want to start the numbering at the closest end to the triple bond. This structure here, we have an alkene and an alkyne. It's 7 carbons long. The alkene is at 1, so we have 1-heptene. So you drop the E. We put 6-ine. This is an ene-ine. You could also name it hept-1-ene, 6-ine. This one here we have the alkyne at the 1 position. This is 4-methyl 7-non-ene 1-ine, or 4-methyl non-7-ene 1-ine. But you don't really need to worry about the ene-ine naming. We won't get that complicated in this class. If you had branching off of a carbon chain, that's based on how many carbons there are. So for 4-carbon straight chain group, this is a butyl group. You can have a butenyl group. So if there's a carbon double bond here, or a butynyl. So you can take this time to try your hand at naming these, and then just come back for the answer momentarily. The first one, we're going to try numbering. I can already see that this alkene is going to get the lowest numbering if we're starting from this end. So I'm going to start with 1, 2, 3. So this is going to be a 2-heptene. I have 3 methyl groups at 2, 6, 6. So that will be trimethyl. In this structure here, I can number it going this way. So my 1 and 2 are contained within the double bond. My methyl groups are at 6. If I number in this direction, my 1 and 2 are still going to be where the double bond starts, but now my methyls are at 4. So I'm going to go with that numbering. So we'll have 4,4-dimethyl cycloheptene. And with these, you don't need to indicate where the numbering is. It's always assumed that it's between 1 and 2. This structure here, I have 1. The numbering puts the alkyne at 4 in both directions, but I have these substituents here that should get the lower numbering. So I'm going to use this numbering to get 3,3-dimethyl 4-octine. And here are some problems where you can practice drawing the structures. 2-methyl hexa 1,5-diene. Hexa tells us I have 6 carbons. Diene means I have 2 double bonds starting at 1 and 5. And 2-methyl, there's a methyl group at 2. So that's how you would draw that one. For 3-ethyl 2,2-dimethyl hept-3-ene, I have hept is 7 carbons. The alkene starts at 3. I have 2 methyls at 2. And at 3 I have an ethyl group, which is 2 carbons. Pentadiene. I have 1, 2, 3, which is where the other alkyne starts. And I need 1 more carbon, 5. So that would be 1,3-pentadiene. And then when you're drawing your alkynes, be mindful of your bond angles. If we look at the electronic structure of alkenes, they have pi bonds and a sigma bond. P orbitals are parallel to each other, and if you break them, if you rotate them, the pi bonds are going to be broken. So there's no carbon-carbon bond rotation in an alkene. We have sp3 hybridized carbons. we have sp2 hybridized carbons, and those form the sigma bond, which is the first one. Second one is a pi bond, and our bond angles are 120 degrees. We can have cis and trans isomers of alkenes. So we saw cis trans isomers in cyclohexanes. Alkenes are going to be the same thing. When you're doing this, you can imagine putting the presence of a carbon-carbon double bond can create two possible structures. In this structure here, you can imagine looking at the first double bond. So I'm going to slice this in half and then compare the groups in terms of size. So which of these is bigger? Is carbon bigger, which has a bigger atomic number? Carbon has an atomic number of 6. Hydrogen is 1. So this is the larger group. On this carbon here, the carbon again has the larger group versus hydrogen. And then if I lay a pencil over the top of the double bond on your paper, you can see that both of the circled groups are on the same side. This makes it a cis isomer. So this is two similar groups on the same side of the double bond. So when we name this now, before it would just be 2-butene, but because we have this information about cis, that tells us it is a cis 2-butene or a cis but 2-ene. This one here, again, if I slice my double bond in half, I'm going to compare the sides here. The CH3 is bigger. On this one, carbon versus hydrogen, CH3 is bigger. Now if you lay your pencil over the top of that double bond, the groups are on different sides of the pencil. One is coming off of the top, one is coming out of the bottom. So this becomes trans 2-butene. So a trans isomer is one where similar groups are on opposite sides of the double bond. So in order for an alkene to have an isomer, there has to be two different groups on the end of the alkene. For example, if I look at this carbon on this end right here, this hydrogen is the same as this hydrogen. We can't pick which group is larger or smaller because they are the same, so that is not going to have a cis-trans isomer. And a cis-trans isomer requires that the end groups differ in pairs, so the bottom pair cannot be superimposed without breaking the carbon-carbon double bond. So in these first ones here, if we flip this one over, we would get this structure. So these two are identical. If I flip this one over, these are not the same. The only way that I can make them the same is by breaking bonds. So on the first one, A is next to D, or on the same side of the double bond as D. And on this side, they're on opposite ends. The only way that we can make them the same is by breaking bonds and doing a rotation. That makes them stereoisomers of each other. If you remember that definition, the stereoisomer has the same formula. They're connected the same, but they differ in 3D space. So on this first carbon here, A and B are connected to the same carbon. A and B are connected to the same carbon, but they're on opposite sides of that double bond, which makes them a stereoisomer. Okay, some places that you might have seen cis and trans alkenes are in trans fats. Most oils are liquids at room temperature, and fatty acid components may have many carbon-carbon double bonds, which are hard to stack because they're polyunsaturated, meaning that they have several double bonds. And then if you look at fats, like butter, these are usually solid at room temperature. They have less carbon-carbon double bonds, and they can stack together, which increases their melting point. So they're said to be saturated fatty acids. So butter is a saturated fat. Oils are unsaturated. So if you think of vegetable oil, that is liquid at room temperature. So these ones have low melting points. This is higher melting points. The saturated fats can stack if you had a saturated fatty acid. They have carboxylic acids with a long carbon chain. These can stack very well together and have several intermolecular interactions, whereas a fatty acid like this one, this oil here, has two cis double bonds, so these don't stack as nicely, so they don't have as many intermolecular interactions, which lowers their melting point. Partially hydrogenated oils are oils that are created from partial catalytic hydrogenation, which means that they will get rid of a double bond. So margarine and shortening come from safflower oil or soybean oil, and then they reduce those double bonds so it's more like butter. So before the oil is heated to make it partially hydrogenated, it has a cis double bond, but then it gets hydrogenated and now creates a trans double bonds. All double bonds in naturally occurring fats and oils have a cis configuration, and the trans fats are the ones that are raising health concerns because they raise your LDL and your cholesterol. And the reason for this is if you look at the structure, the saturated fatty acids are able to stack very nicely. This one can also stack pretty nicely. And so you can stack a whole bunch of these in your arteries. So maybe 10 can get in through your arteries. These ones don't stack as nicely because of the shape. It's very kinked and takes up a lot of space. So you might not be able to get as many of these fatty acids through your arteries. So these ones are more likely to clog arteries. The cis ones do not stack as well.